Okay.
Ready?
Yep.
Okay. Today we're going to keep talking about molecular dynamics at surfaces, and the topic for today is going to be we're going to start talking about energy transfer at surfaces. So we were talking about, for example, processes like adsorption of molecules to surfaces. In order for molecules to adsorb on surfaces and do chemistry at surfaces, they first have to dissipate energy. And so we're going to be talking about energy transfer mechanisms between molecules and surfaces. And today we're going to talk about particularly coupling to molecular or degrees of freedom of the solid through phonons, which are basically lattice vibrations of the atoms that make up a solid. Okay, so yeah, when you have a reaction at a surface, energy transfer between the reaction center and the solid is an essential element of the problem. And we can divide the system into two parts, the solid and the adsorbate. So in the particular case of vibrational energy transfer, as physical chemists, we sort of have a good idea how do we talk about the vibrations of a molecule, right, in terms of its normal mode vibrations, but we need to also consider how to treat the phonon vibrations of the solid, right? And so, yeah, basically there's, two primary ways that you can dissipate energy to the surface. You can excite surface phonons, right, or you can excite the electronic degrees of freedom of the surface. You can excite electron hole pairs. So this one we'll talk about next time, and today we're going to talk about phonons. Okay, so we've talked about sort of an analogous problem in the gas phase where you have a collision between gas phase partners and you excite vibration, right? So you transfer vibrational energy. We also looked at least one example where you had near resonant transfer of vibration from one molecule to another molecule, and that was actually much more efficient than transfer of translational energy to vibrational energy. Okay, but in surface dynamics, we're going to consider coupling to the lattice vibrations of a solid. Okay, so what are these things called phonons? Well, if you ask a physicist, a phonon is a quasi-particle. But we can think of it like a vibration of a lattice in a solid. It's kind of like a vibration that takes place, it's like a vibrational mode in a really, really big molecule, right? So big that we can't consider every single atom. We just have to consider them as a, bulk. Okay, so if you consider a vibration of a lattice along with a wave that is propagating in a particular direction, right? It's denoted by the k vector, right? The wave vector. Then you can think of it sort of in terms of this picture, where the light-colored circles represent the equilibrium lattice position of each atom, if you have a square lattice, and then the dark circles represent the instantaneous position of each atom. And so these vectors u sub I represent the displacement of the ith atom away from its equilibrium position, right? So here, u s plus 1 is 0, it's not displaced, but the next atom over, s plus 2, in the s plus 2 position, that one has a displacement u. Okay? And so we can consider the forces acting on a particular atom, S or S minus 1 or whatever. In this picture it's S minus 1, right? And so if you consider sort of the full, in this case, two-dimensional lattice, there's probably forces coming from all different directions, but you can treat these forces effectively, and just for make a simplified model, you can think about just a one-dimensional slice through this lattice that has effective potentials in the left-right direction. Okay, so we're going to treat a one-dimensional lattice. That's how we'll get started. And so the simplest way to treat vibrational motion is to assume a Hooke's law force constant. That's the same thing that we do when we treat normal mode vibration in molecules. And so the force on a particular atom at lattice position S can be written in this form. So it's a sum of a force constant times a difference in the displacement between atom S and atom S plus N. Okay, and so for now this is summed over all of the atoms, right? So the atom S has an interaction with atom S plus 1, S plus 2, S plus 3, right? Also S minus 1, S minus 2, etc. And so if we then apply Newton's law, right, force equals mass times acceleration, then we can write this force constant in terms of an equation like this. So the mass times the acceleration, which is the second time derivative of the displacement, is going to equal the force. Okay, and as a solution to this equation, it's going to have the form of a plane wave. So the solutions for u s plus n, it turns out it's going to have a form that looks like this. It's a prefactor times a complex exponential, right? So it looks sort of qualitatively similar to a light wave, but actually there are differences between phonons and light waves that we'll see a little bit later. Right, so it's e to the minus I omega t plus k n a. So for a light wave, you would have I omega t plus or minus k x, where x is a continuous variable. But here, the x variable is actually not continuous because these displacement quantities only are defined at particular points on the lattice. You have a displacement for each individual atom. So you don't have a continuous variable x, you have n times a, where n is an integer and a is the lattice constant. So each value of n specifies a different atom. Right, so this is the displacement for the nth atom away from atom S, basically. Okay, does that make sense? Okay, and so omega is a temporal frequency. It's how many cycles per unit time, and k is 2 pi over the wavelength of the oscillation. So it's how many cycles do you have per unit distance. Okay, right. So this k 2 pi over lambda is called the wave vector.
Why is n is an integer number?
Because each atom, it refers to the displacement. So for each value of n, this equation gives the displacement of the nth atom. So you have atom S, it has a particular displacement, u sub s. You have atom S plus 1, it has a particular displacement. In this figure, u s plus 1 is 0, u s plus 2 is some, positive number.
Oh, okay, I see.
And so this equation is only defined for integer values of n because each integer value of n gives the displacement of the nth atom, or the s plus nth atom. Does that make sense?
Yes, and then the explanation of why the atoms go inside of each other. Or,
Go what?
I mean, because they are connected like that, and then how can I avoid that the movement of this atom can collide with the other here?
Oh, well, yeah, we're assuming.
How can I limitate
I mean,
this
if you
X
assume,
value?
we're assuming relatively small amplitude vibrations. So we're assuming that each atom stays in its lattice position. It doesn't move to the other side. They don't swap places.
Oh, okay, makes sense.
Otherwise, you would need, I mean, if you want to go to high enough energies where they're swapping places, then you start having effects like melting and stuff like that. And then the lattice picture sort of, you have to throw that out. And you have to start thinking about it more like a liquid. Okay, so the next thing that we're going to do, we plug this equation into our Newton's law equation. And so if we plug in mu s here, right, then we're going to get, right, so plugging this in to the second derivative here, we're going to get minus I times omega quantity squared, which gives us minus omega squared, right, times the mass times this function. And then on the left-hand side, or I'm sorry, on the right-hand side of the equation, we get us plus n minus us. So we get this equation here for s plus n, and then we have to also add this equation with n equals 0. Okay, and then we divide both sides of the equation by u, right? So the u's cancel. We divide both sides of the equation by this complex exponential. The first term here cancels to give 1, and the second term, the omega part cancels, but we get left with an e to the I k n a. Okay? And so then, so far, we're including the interaction between atom S with every single other atom, right? So n goes from minus infinity to plus infinity. But in principle, in general, physically, the strongest interactions are with the nearest neighbor atoms. The next nearest neighbor atoms have a much weaker interaction, and as you go 2 or 3 atoms away, the interactions get weaker and weaker. So as a simplifying approximation, we can include only the nearest neighbor interactions. So that means n equals plus or minus 1, right? So we're going to consider the s plus 1 atom and the s minus 1 atom. And by symmetry, the force constants are the same, c minus 1 equals c1. And so if we evaluate this for n equals minus 1 and n equals plus 1, then we get an e to the ika and an e to the minus ika. And we get two factors of, or two ones, right, added together, right, when we sum it up. And so using a trig identity, right, this e to the ika plus e to the minus ika, that equals 2 times cosine of ka, right? So we can substitute a cosine here. And then using another trig identity, 1 minus cosine of x equals sine squared of x over 2. And so finally, we can solve for omega by taking the square root. And this is the expression that we get. So this is what's called a dispersion relation, which relates the frequency, omega, to the wave vector k. And so you can see already that there's a difference between the behavior of a phonon and a photon, because in photons, the wave vector is linearly proportional to the frequency, whereas in a phonon, this relationship is nonlinear, right? You have this absolute value sine function, right? So it's going to be actually linear at low k, but nonlinear at high k. Okay. So, before we start thinking about that, first we can talk a little bit about, what are these plane waves? What does that mean in terms of what's happening in the solid, right? So, this equation describes a vibration that has a certain frequency and it has a certain wavelength that is related to 1 over k, right? So 2 pi over k is the wavelength. And so, basically, you can think of this in terms of, if you think of the solid as like a really long linear molecule, then that would have normal modes of vibration, and those are analogous to the one-dimensional phonons on a 1D lattice. And so you can have a phonon with a long wavelength like this one, where here the atoms are a little closer together, here they're a little bit further apart. Or you can have phonons with shorter wavelengths, so you have a compression, rarefaction, right? Or you can have shorter wavelengths, right, where you have only 3 atoms close together, 1 atom far apart, further apart, and so forth. But there is a minimum wavelength corresponding to a maximum phonon frequency that occurs when the wavelength is 2 times the lattice constant. So when every other atom is vibrating in the opposite direction, that is the highest frequency phonon that you can have. So there's a frequency cutoff to this problem, and you can think of that as, it's kind of like if you think of this as a really long molecule, then this is the normal mode with the maximum vibrational frequency. Okay? And so, yeah, this maximum frequency occurs when k equals pi over the lattice constant. Okay, any questions about that? Okay, so we also derived just a couple of slides ago this dispersion relation, which gives the relationship between the frequency omega and the wave vector k. And so if you plot this function, it's proportional to an absolute value of a sine. And so it looks like this. But like we said, the phonons have a maximum frequency when the wave vector equals pi over the lattice constant. And so you don't have to consider this function for every value of k. It's sufficient to only consider the values between minus pi over a and pi over a, which is in this light shaded region here. And this is called the Brillouin zone. Okay, so you can just think of this part here. And so, like we said, at long wavelengths, right, corresponding to low frequencies, these phonons behave kind of analogously to photons because the omega is linearly proportional to k. But at shorter wavelengths, right, corresponding to longer or larger wave vectors, the curve starts to be nonlinear, and you have some behavior that's a bit different, right? And then you have a hard frequency cutoff, right? And that's just due to the discrete nature of the lattice, right? Okay, so far we've just been considering one dimension of motion, but if you have 3 dimensions of motion, and if you consider a plane wave propagating in a linear direction, then you can actually have 3 different branches. One branch corresponding to longitudinal type of motion, where the displacement of the atoms is along the same direction as the propagation of the wave. And then there are 2 branches that have transverse displacements, where the displacements of the atoms are perpendicular to the propagation of the wave. So you can have one transverse wave in the y direction and one transverse wave coming out of the plane of the screen in the x direction. Right? And so in principle, these can have different frequencies because the force constants for motion in this direction can be different than the force constants for motion in the transverse direction. And if you sort of make an analogy to molecules, this would be kind of like stretching modes of a linear molecule versus bending modes of a linear molecule. Okay? And so if you draw so here's the dispersion curves for copper along the 1, 0, 0 direction. And you can see there's a longitudinal mode, right, that qualitatively looks like this sine function. And then you also have a doubly degenerate transverse mode, which is lower in frequency. Okay, so that's if you have just a one-dimensional lattice of atoms, right? Or if you just consider one, possible direction of travel. But in a 3-dimensional crystal, the situation is actually more complicated. I'm not going to go into all the detail about this, but just to give you a flavor of what's going on. So in one dimension, the dispersion relation looks like this. You can plot it on a x, y graph. But in 3 dimensions, the Brillouin zone is not a one-dimensional object, but it's a 3-dimensional object because you can have a k vector, a wave propagation vector, in each of the 3 dimensions of space. And so instead of a region, you get sort of a box, right? And then there's, due to the crystal structure, the Brillouin zone has different cutoffs in different directions. If you want to understand everything about this, we don't have time to talk about it. You have to take a solid-state physics course. But when people do phonon calculations, typically the way that the results are displayed so that you can visualize it more easily is to look at cuts of the dispersion relation through high-dimensional directions of phonon propagation. So for example, here are shown, this is the dispersion curves for copper right? So wave vector on the x-axis and frequency on the y-axis. And you can see here's what the dispersion curves look like through the 1, 0, 0 direction. Here's what it looks like in the 1, 1, 0 direction. And here's what it looks like in the 1, 1, 1 direction. And so you can see in this direction and this direction, the two transverse modes are degenerate, but along the 1, 1, 0 direction, they're actually not degenerate. They have different frequencies. Okay, so what happens if you have a more complicated type of solid? So if you have a crystal that has two different types of atoms, like say you have sodium chloride or something like that, then the problem is a little bit more complicated, but you can treat it in an analogous fashion. But you get two different equations of motion, one for the second derivative of the A-type atoms, one for the derivative of the mass times acceleration of the B-type atoms. And they can have different masses, and also there can be different force constants for AA interactions versus AB interactions versus BB interactions. And so I'm not going to go through all the math, but if you do this, you actually end up with a dispersion relation that looks like this if you use a simple next neighbor model. And so there's two different frequencies here, notice. So one with a minus sign and one with a plus sign. And the minus sign corresponds to what's called an acoustic branch of phonon, and the plus sign corresponds to what's called an optical branch. Okay, and so if you look at the dispersion curve, the acoustic branch, the one with the minus sign, it goes to 0 at k equals 0, so it looks qualitatively similar to the phonons in a monoatomic crystal, whereas the optical branch, it looks a little bit different. This is kind of a new phenomenon where the frequency is non-zero at all wavelengths, at all wave vectors. And so just qualitatively, what types of motion do these two types of waves correspond to? Well, the acoustic waves look like this one, where each neighbor atom displacement is in the same direction. Whereas the optical waves, they look like this picture here. And this involves a situation where the A atoms are vibrating in an opposite direction from their neighboring B atoms, but in a wave that has an overall wavelength that could be, multiple lattice constants long. Okay, and so the reason for the names, it's called an acoustic wave because this type of wave is what a sound wave looks like in a material. And these ones are called optical waves because in many cases they can be optically excited by photons. Okay, any questions about that? Okay, and so if you look at dispersion curves in a real material, so here are the dispersion curves for lithium fluoride, and they look a little bit more complicated than the dispersion curves for copper, because you have both these acoustic modes that go to 0 at when the wave vector is 0, and you have these optical modes or optical branches that do not go to 0. Okay, but qualitatively it looks kind of like the copper picture, except you also have these optic branches. Okay, and so the picture looks more complicated, but notice again there is a maximum frequency in the diagram, and so that corresponds to the maximum possible phonon frequency. Okay, and so that brings us to the Debye model for the phonon spectrum. So one thing that's really important for the interaction of, or the energy exchange between phonons and molecules that could be doing chemistry at a surface is what is the density of phonon modes at a particular frequency. And so the simplest model for that is called the Debye model, or well, the simplest useful model for that is called the Debye model, I would say. And so if you consider a cube with side length L, then the resonating modes inside the box, right, that obey the boundary condition that the displacement has to be 0 at the edge of the box. You would have wavelengths that have to be 2L over n, where n is an integer, right? So that's just the formula for standing waves, right, of a certain length. And the three-dimensional analog of this equation looks like this. So nx squared plus ny squared plus nz squared has to be 4L squared over lambda squared. Okay? And so if you make a simplifying approximation that the dispersion relation is linear, which it would be at low frequencies, then you can substitute lambda equals the speed divided by the frequency. Right? So this is like, you know, if you're probably familiar with dealing with light waves where the frequency is c over lambda, right? So that's basically what we've done. So w is the speed of propagation, and lambda equals the speed divided by the frequency. Is that okay? Does that make sense? And so this is actually not a rigorously true equality, but this is an assumption that's made in the Debye model. And it's true for describing the low frequency phonons. Okay. Okay, so we want to know what's the density of states at a certain frequency, or the density of phonon modes at a certain frequency. And so if we take this formula here and rearrange it, we can divide by the right side of the equation, and this is what we get. And this is actually the equation for a sphere of radius 2L nu over W. And so it has the volume of 4/3 pi times r cubed, right, which is this. Okay? And so if we draw this sphere, right, it has, you know, it has x, y, and z radii, nx, ny, and z. Or, you know, nx equals this radius L nu over W, right? That's the radius of the circle in nx, ny, and z space. And so each set of positive integers, nx, ny, and z, would represent some allowed standing wave in 3 dimensions, which in this picture where you have this sphere in nx, ny, and z space, that would, you know, each vibration would correspond to a cube of volume 1. And so if you add up, you know, what's the total number of states with, you know, quantum numbers nx, ny, and z that you could have equal to or below some frequency nu, that would just be approximately equal to the volume of the sphere. Okay, so this is the total number of states, is this volume of the sphere. And what we want to know the density of states, which means the number of states between frequency nu and nu plus d nu. And that's equal to dz, which equals the derivative of this z, right, the total number of states with respect to nu times d nu. And so all we need to do is take the derivative of this equation here, right, with respect to nu. So it's a constant times nu cubed. So we're going to get a factor of 3, and then we're going to get nu squared. And so, yeah, 4 pi nu squared over, this should be a w, sorry, w cubed v. And I've substituted L cubed equals volume. Okay? Any questions? Okay, so basically the key result is the density of states is proportional to the frequency squared. Okay? And so, so far we've been considering a particular dispersion relation, right, between the between the wave vector and the frequency, right, which gave us a certain speed of propagation w, but like we saw, there's different branches that you have to add together, and so if you have a monoatomic FCC crystal, then you have to consider 3 branches, 1 longitudinal and 2 transverse. And for the FCC crystal, the transverse branches were degenerate. And so if you add the 3 branches together, you get 1 over the speed of propagation for the longitudinal branch plus 2 times the propagation speed for the transverse branch, right, adding the 3 together. And then if you sort of substitute a weighted average speed, right, a weighted average group velocity for the propagation, that would be W bar, then you get this expression here, which is basically this one times 3, and we've just substituted, instead of W, we have an average value of the group velocity. Okay? And so this is the density of states, but remember the wavelength has to be longer than 2a, and so there's a maximum allowed frequency. And so the total number of degrees of freedom should be 3n minus 6, but if you have a macroscopic solid, n is a really large number, it's like 10 to the 20, and so 6, doesn't matter, so it's approximately 3n. And so we can say the number of degrees of freedom is equal to the total number of vibrational states, which is the density of states integrated over all possible frequencies, right? So number of states at each frequency integrated over all the frequency. Okay, and so if you take this expression here and you integrate it from 0 to the maximum frequency, then basically you just get a constant, right, times mu squared, and you have to integrate mu squared from 0 to Vmax. That gives you Vmax cubed over 3, and so this is the expression that you get. And so basically if you take this expression here, which we got from this integral, solve it for the average group velocity, W, then you get this expression for W, and if you take this expression for W and plug it into our expression for density of states, then you can get the desired expression, which is 9n times nu squared over nu maximum cubed. Okay, and so that gives you the density of states as a function of frequency. So the density of states increases as the frequency squared. And so it looks like this kind of parabola, but there's a maximum frequency that you can have for the phonons. And so the parabola cuts off at a particular frequency. Okay? So that's the Debye model. If you look at real solids, they can have a more complicated phonon structure than this. This is a very simplified picture. So if you look at a real solid like silicon, it actually, due to these different branches with different frequencies, it can have a more complicated structure. You do see that there is this nu squared behavior at low frequency, right? So that's described correctly by the Debye model. And what's also described correctly is that there is a maximum frequency after which the phonons get cut off. So, here the maximum frequency would be at around 15 terahertz. Okay, so that is basically a really quick introduction to phonons. And now I'll talk a little bit about interaction of phonons with molecules. And I'll do that via an example. So we'll look at an experiment that's been done where a molecule, methylphthalate, is absorbed on a silver surface, and then a pump probe laser experiment is performed on the molecule. So there's a pump laser, an infrared pump laser that comes in, and it excites the CH stretch of the molecule, which is at about just a little bit less than 3,000 reciprocal centimeters. And that's excited by a picosecond laser pulse. So we can, with these picosecond laser pulses, we can see dynamics that occur on a picosecond time scale. And then you come in with a second laser in the visible, and that laser also has a picosecond pulse length, and it's used to probe in the time domain the excitation in the CH stretch. And it uses a method called sum frequency generation, which basically means you excite a particular vibration with IR, then you come in with a visible photon, and if the IR excitation is still present when the visible photon reflects from the surface, then you can have this nonlinear sum frequency generation process where the scattered photon basically takes the IR energy away from the molecule and it goes into the photon, so you get a sum, a photon reflected from the surface has the sum of the energy of the IR and the visible photon. You can think of it a little bit like an anti-Stokes Raman process, right? And so normally in Raman spectroscopy, right, you come in with a visible photon and then it scatters at a lower photon energy because the system gets vibrationally excited. In this case, it's the opposite process. So if the system is vibrationally excited, you can come in with a visible photon and then you'll see the sum frequency emitted. Okay, and so if you emit the sum frequency, you can detect that on a detector. And if you scan the frequency of the infrared laser, then you can get in what's called an SFG spectrum, right? Sum frequency generation spectrum of the molecules on the surface. So if you scan the frequency of the infrared laser, at some frequencies the infrared laser is not resonant with the molecular vibration, so you don't see any signal. But when the infrared photon is resonant with an absorption, then you can see the visible light being scattered at a higher photon energy, and then you see a signal on the detector. And so you get a spectrum of the vibrations on the surface. Okay, so that would be a frequency domain spectrum, or a frequency domain experiment. But in the time domain, what's going on? So if you park the infrared laser at a particular frequency, and then scan the delay time between the pump laser and the probe laser, then you can get a decay profile. And here's what the decay profile looks like. So this is the sum frequency generation signal as a function of the delay time between the two lasers, right? And so the signal that is observed has a bi-exponential decay. It's got a short, a fast decay component that's shorter than 5 picoseconds, right? So here it says it's about 3 picosecond. So it's, almost too fast to measure. It's on the same time scale as the laser pulse. But then it's got a slow decay, which has a time scale of about 63 picoseconds. Okay? And so what is going on here? So one thing to keep in mind when thinking about molecular vibrations at surfaces is that a typical phonon cutoff energy for a crystal is a very low frequency relative to molecular vibrations that we're used to thinking about, because usually the lattice interactions between atoms in a solid crystal are relatively weak. They're weaker than covalent bonds in molecules. And so if you look at the energetic picture, the Debye frequency for silver is only 145 reciprocal centimeters, whereas the CH stretch that we excited was up around 3,000 reciprocal centimeters. And so in order for, this vibrational energy is not resonant with the phonon energy. So you would need something like a 20 phonon process in order to directly transfer the energy from the CH stretch to the phonons of the solid. And so that process is really inefficient and it does not happen. So instead, the behavior is attributed to an intramolecular vibrational redistribution mediated relaxation process. So you remember IVR is the process by which energy can be transferred from one mode of molecular vibration to another. And so on fast timescales, there's the vibrational energy equilibrates between a small number of strongly coupled modes, right? So that's why the signal decreases a little bit on a very fast time scale. And so probably this involves the different CH stretching modes, right? Because there's, in SCH3, there's 3 CH bonds, and so they can couple to make different stretching modes. Right, so I've sort of drawn that as a cartoon here. These are not the exact frequencies of the molecule, it's just a sort of cartoon picture for what's going on. So on short time scales, the energy sort of gets equilibrated between these small number of modes, so it doesn't decay irreversibly, but it decreases because it gets dispersed between different modes. On slightly longer time scales, the stretching motion can get coupled to things like bending vibrations, which are going to have a frequency of somewhere around 1,000 reciprocal centimeters, right? So this would be maybe well, the way it's drawn here, maybe it's a 3-to-1 process. Maybe there's some more modes that are here, so you can have a 2-to-1 process, right? So you excite 2 modes of some bending vibration with 1 mode of a stretch. And then on longer time scales, the vibrational excitation can couple to torsional modes at lower frequencies. And then these torsional modes can couple to the phonon modes of the solid via 2-to-1 processes. So you can excite approximately 2 quanta of phonon vibration with 1 quantum of molecular torsion. If the torsions are about 300 wave numbers and the Debye frequency is about 150. Okay? But direct transfer of 3,000 reciprocal centimeters of vibrational energy from the CH stretch directly to the surface phonon would be a 20 phonon process, and so it's really unlikely. And so that's the reason why this decay happens on a fairly long time scale for vibrational motion, right? A vibration takes about, femtosecond. So picosecond is like many, many vibrations of the CH bond before it gets dissipated into the solids, right? The CH bond stretch has to vibrate, over 1,000 times before it can lose its vibrational energy to the surface. And the reason is because there's an energy mismatch. Okay, I think that's about all that we have time for. So next time we'll talk a little bit about electronic degrees of freedom, a little bit about dynamics in solution phase. I wanted to have a little bit more time for this topic, but things always take longer than expected. Today, the building closes at noon, so I will not be in my office.